Good afternoon, everybody, and welcome to Indian Association for the Cultivation of Science. So I will invite our director, Professor Tapas Chakraborty, to tell you a few words about IACS, and then, of course, we begin our usual lecture. Okay, so Professor Chakraborty.
Okay, thank you, Professor Dasgupta. And good afternoon, Professor Ramasesha, Professor Yoshikawa, and all the participants of this workshop on computational methods. On my behalf, I welcome you to this afternoon session. Now, IACS also have a number of strong computational groups who are doing computational physics, computational chemistry, and computational biology. So possibly some of them are also giving lectures, and maybe this afternoon. Yes. So, and I hope that you are enjoying your workshop. Now, Indian Association for the Cultivation of Science, presently, it is a deemed to be university, possibly one of the smallest and science research university and the newest university of this country. So we have undergraduate program, master's program, as well as PhD program. The institute started its journey long back. In fact, this is the first research institute of this country. And it was founded as a mark of cultural revolution and renaissance of this region of the country in the 19th century, particularly in the second half of this 19th century. People equipped with this Western education, they felt that we should also have an institute of this country to carry out research, particularly this Western research, or more precisely, more like this European research. So with that idea, it came up in 1876. And then many of you know this name of this Professor C.V. Raman, that who worked here. And basically, he built here the research base of this institute that started from 1907. And he built also a very strong physical science group in this part of the country. So at this moment in this university, we have school structures, School of Physical Sciences, Chemical Sciences, and Mathematics and Computational Sciences, Biological Sciences, Material Sciences, and Interdisciplinary Sciences. We have about a little less than 70 faculty members at this moment, but number of PhD students is more than 500. So per faculty, PhD student is still possibly the highest in this country. And so with this brief introduction about our institute, I again welcome you here to this second half of this workshop, and I hope that you will enjoy. Thank you.
So thank you, Professor Chakraborty, and with much ado, I invite Professor Ramasesha for his final talk on DMRG. And I think the duration of the talk is 1 hour, 15 minutes. And you already heard the first two parts of the talk, and the third part he will be presenting now. Can you please share the screen?
For online one Prof. Huh? Yeah, no problem. I can overshoot it. Okay, thank you very much, Professor Dasgupta. And it's indeed nice to be here again. I've been here several times. And now I'm going to be talking about how to do dynamics with density matrix renormalization group technique. Yeah, okay. Once again, let me use my pointer because it's too faint. Okay, we are now going to be talking about how to do dynamics with the DMRG. So often there are two types of dynamics when people talk about. One of them is the frequency dependent properties. Example of properties which are frequency dependent, and of course linear and nonlinear optical polarizabilities. It was in this context that we started doing DMRG. And then you have inelastic neutron scattering if you want to do to get spin wave spectrum and so forth. That's useful. Optical absorption, photo emission, these are some of the frequency dependent properties that one is interested in. And as far as time dependent properties go, the kind of time dependent properties that people are interested in are transport properties in nanoscale systems, and also spin charge separability, one of the things that people have been quite interested in. And let us see how one can do it. So as far as the frequency dependent properties are concerned, you are interested in the spectral function, because the spectral function is going to give you the spectral weight as well as the energies of the excited states. And that is given by -1 by pi imaginary part of this quantity, psi O dagger 1 by z minus I omega minus h O times psi naught. So O is a property, operator corresponding to the property that you are interested in, whose spectral function you want to compute. And of course, if you use the Cauchy principal value, 1 upon x plus I epsilon can be written as principal value of 1 by x minus I pi delta x. And if you use this, you can always write I omega as sigma over n psi n O psi 0 squared E n minus E 0. This gives you, for example, the oscillator strengths for excitations in molecules, or it also gives you the frequency dependent response corresponding to the observable O. And one of the examples of frequency dependent properties is polarizability. Polarizability, if I write down explicitly the expansion from here, then what you have is an expansion over a transition dipole moment between ground state and an excited state, and back. This is a second order perturbation theory divided by the energy denominator. So this gives you alpha Ij as a function of omega. Often people are interested in computing these quantities. You see, if you look at this expression, it is a sum over states. So everything can be reduced to a sum over states expressions, and the sum over states can be evaluated if you know the ground state from the DMRG, say, and you know the excited states from the DMRG, and you can also know if you know the eigenstates, then you can calculate the transition dipole moment elements, and the summation is over all excited states of the Hamilton. You can explicitly compute it. But this requires all excited states and dipole matrix elements from ground to excited states. So the DMRG that you have, you can only get a few excited states. You never compute all the excited states. So if you compute like 20 or 30, it is not enough. And incidentally, in most of the quantum chemical literature, if you look at it, then people compute about 30 excited states or 40 excited states using configuration interaction techniques, and then compute the transition dipoles and then explicitly do the sum over state. That is a very poor approximation, because it is an uncontrolled approximation. Where you are going to truncate is completely left to you. And also you leave out much of the excited state space, so it's not great. But still widely used in quantum chemistry for estimating frequency dependent polarizabilities, both linear and nonlinear polarizabilities. So Karen Hallberg introduced the Lanchos methods into density matrix renormalization group techniques. And just to recap, the Lanchos method, if you want to know the ground state eigenfunction, then you have this Hamiltonian H, some arbitrary vector B, B1. Then you from that you generate two matrix elements H11, H12, and you also generate a second basis vector B2. Operate on the second basis vector B2, you generate another new basis vector B3 and the matrix element H21, H22, H23, and so on and so forth. And you can get a R by R matrix, which is tridiagonal. You can get a solve for the eigenvalues and the eigenfunctions. So this is what we did in the previous lecture. Now, we want to set up, we obtain the ground state first, and then we want to know how to calculate the nonlinear optical property or the frequency dependent property. So for that, what you do is the following. You first get the ground state using the Lanchos algorithm. Once you get the ground state, then you form this function, which is O times psi 0. Okay, let me go there. So you form the function phi 0, which is O times psi 0 divided by, of course, the normalization of phi 0. Okay, so you normalize phi 0 and then you get this function. Now you can set up the matrix using starting with phi 0. You can set up the Lanchos matrix as before. Okay, because we did that before, but we did that with an arbitrary initial state. Now what you are going to do is obtain the ground state, operate on the ground state by O, and then use that state to generate the Lanchos matrix. Okay, so once you get the Lanchos matrix, then you consider the following identity, which is just, Z minus H inverse, Z minus H is equal to identity. Just product of a matrix multiplied by its inverse always gives you the identity. And I'm just expanding it and writing, which is sum over the index n, just a second. See, this summation should be over m, not n, not m, because the common index is n. So I'm sorry, I made a mistake. Sum over n, Z minus H inverse mn, Z minus H np is delta mp. Okay, so that is nothing but getting the matrix element of the product. Now, for m equal to 0, or rather p equal to 0, you can write down explicitly the equation, which is Z minus H mn, and I call xn the matrix element which was here. This matrix element, which is corresponding to p equal to 0, I call them as xn. Okay, so times xn is equal to phi naught Z minus H inverse phi naught. Okay, where x naught is this quantity. Right? Do you follow that? So this is what I have written, just explicitly the same expression as the previous one, except I called the second element as xn, and this is equal to delta m0, and when m is equal, when n is equal to 0, x0 is this quantity, phi naught z minus z to the z minus h inverse phi naught. So now I want to calculate x naught. To calculate x naught, what I'll do is the following. I'll take p equal to 0, and so this is a set of linear equations. So what are these linear equations? Z minus h 0 0 up to HRR is x naught. That's times x naught is 1. That is our first equation, right? Because, and the second one is h01 z minus h11 0, and the third row, etc. And then the vector here is x naught, x1, etc. because that is the xn you have. And the right side is delta m0. So only the first element is 1 and all the others are 0. Okay, so these are a set of equations you really have to solve. And solving this set of equations is quite simple because you just use Kramer's rule for solving the inhomogeneous linear algebraic equations. You can do that. And once you get x0, then you know it is phi 0 z minus h to the inverse phi 0. And we already know that phi 0 has a O psi naught. So because of that, if you look at, if you substitute back into this expression, you have seen O0 psi naught, O dagger psi naught on the left side, and you have 1 upon z minus I omega h here. So what you are going to get is actually the power spectrum. So x0 corresponds to the power spectrum. Okay, so this is the x0 and it corresponds to the power spectrum. And the only drawback is that the Lanczos matrix usually you set up are pretty small, never more than 100 by 100 or so. In fact, if the matrix size exceeds 100, you go back and use the first vector, the eigenvector of the 100 by 100 matrix as phi 0 and restart your calculation. So that's what's done in Lanczos. So you never use more than about 100 states. Okay, even though those 100 is much larger than 30, but still it is not a great technique. The only good thing is that once you have this matrix, you can calculate the power spectrum for all values of omega. You just fit in different values of omega and you can calculate the power spectrum. So we came up with a different technique which is known as a correction vector technique. This was invented when we were working on exact diagonalization for computing nonlinear optic properties of molecules. So in this, what you are going to do is you define the first order correction vector phi 1. So what is phi 1? Phi 1 is nothing but the solution of this equation h minus E naught plus h cross omega. Phi 1 omega is O operating upon psi 0. Okay. Now, what exactly is phi 1? You can also look at it this way. Let me say what I can do is I can expand phi 1 in a basis like a valence bond functions or Slater determinants or whatever you have. So once you expand that in a basis, then you can represent your Hamiltonian is also in the same basis, Hij, and O times psi naught can also be expressed in the same basis, in which case this equation that I have written here becomes a linear algebraic equation again, Hc equal to B. H is the Hamiltonian in the basis of the functions K. C is the correction vector in the basis of K, which I want to find out because I need the coefficient Ck, and then P is the inhomogeneous part of the equations. So the point is actually what is phi 1? So if you want to know what phi 1 is, let me look at the eigensystem H psi k is equal to Ek psi k. Now, instead of expanding phi 1 in terms of the basis vectors, if I chose to expand phi 1 in terms of the eigenstate psi k, which is sigma over k fk psi k, and I want to find out what is fk. Okay, so if I want to find out what is fk, then I'll just take an inner product with the eigenstate psi l to find out fl. Okay, so psi l inner product from the left side on both sides I take, then what I get is psi l h minus E0 h cross omega psi k fk is equal to this quantity. Now H can operate, is the Hermitian operator, the Hamiltonian, so it can operate either on the right or on the left. So if it operates on the left, you get EL H psi L will give you EL psi L, and psi L and psi k are orthogonal because you know that H is Hermitian, so you can always choose eigenstates of the Hermitian operators which are orthogonal. So because of that, I'll have FL here. So or in other words, FL is equal to psi L O psi 0 divided by EL minus E naught plus H cross omega. Okay, so now you see that my correction vector is nothing but this quantity is times the eigenstate. So if I want to find out what the polarizability is, for example, alpha ij omega, all I need to do is use for the operator O the transition dipole operator or the dipole displacement operator. If you use a dipole displacement operator, and let us say that you use a component I of the dipole operator here, and then you get if you use the component J of the dipole operator, then you will get phi j1 omega, and then you take the matrix element of phi j1 omega with the psi 0 ground state of the operator mu I, then what you will get is alpha ij omega is equal to psi 0 mu I phi j1, and the expression for alpha ij will just become 1/4 this matrix element plus this matrix element. So for example, I'll just go back and show you what we actually mean by that. See, you have the energy denominator, which was there in the function P1, and you had one of the transition dipoles in the function P1, because P1 was this function, G mu I R divided by the energy denominator. And then you are taking times R. And so now you are taking the matrix element of mu J with the ground state between P1 and the ground state. Okay. And the other one is just for the minus omega. So you will get, using that, you can get the polarizability. This one. Okay. So using that, you can get the polarizability. So you can continue with this one. That is, you can also define a second order correction vector. The second order correction vector will be phi2 omega 2 omega 1, because I'm going to be operating by O on phi1 omega 1. So omega 1 is already there, and the operator on the left side is h minus e naught plus h cross omega 2. So phi2 now is a function of both omega 2 and omega 1. So there are two frequencies there. So I can calculate again this quantity. If I do the calculation of phi2 can be shown to be a double summation over the excited states of the Hamiltonian. So you can write down explicit expressions for things like the second harmonic generation coefficient, like beta ijk. Okay, this is actually the sum frequency generation that I'm rewritten. So this is some permutation operator, because in nonlinear optic coefficients you get the permutation operators because you have the electric fields which can operate hit in at different times. Okay, so you have this part is going to be the expression for beta ijk, and P is a permutation operator which permutes I and minus omega 1 minus omega 2, that is I comma minus omega sigma, and then j comma omega 1 and k comma omega 2. So these permutations are included here, so there are 6 of them. And you can also compute the explicit this thing explicitly, the third harmonic generation coefficient. So here I have omega 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 third harmonic generation coefficient, and this is the expression for that, which uses P2 and P1 both. So you have P2 some place and P1. I don't know why my eyesight is failing. Okay, so this is the expression for that. Okay, so and I have given the energy denominators here. This is the sum over states expression, and this is the expression in terms of the P2s. Okay, we can employ the renormalized Hamiltonian matrix from the DMRG method. Okay, so DMRG method, the Hamiltonian matrix is usually of the order of 1,000,000 by million. Okay, so when you are actually doing a Lanczos calculation, then you are not taking all the million excited states, you are only taking about 100 excited states. But in our case, implicitly we would have taken all the million excited states, and this method is much more accurate than the Lanczos method. And you can construct the average density matrix, but when you are doing the DMRG calculation, you can construct an average density matrix both from the ground state and the correction vector. So you can use the correction vector, write down the density matrix from there, and then get the density matrix also from the eigenstate, and you weight them and mix them, and then take the average density matrix and their eigenfunctions as the basis vector. So that can be done. So this method implicitly includes all the excited states. The method is much more compute extensive than the Lanczos method, because for every frequency omega, you have to solve the linear equations. Okay, so that's the reason why it's more compute expensive. And it involves solving large inhomogeneous linear algebraic equations, extensively used in dynamics using DMRG method. And we have applied this to obtain second harmonic and third harmonic generation coefficient and 2-photon absorption cross section. Now, I just want to give you an algorithm for solving huge system of linear algebraic equations. We have solved systems which are more than 1,000,000 equations. And how does one do it? again, similar to the Davidson algorithm, because Davidson algorithm is for the eigenstate, and this method that was developed by us is for the system Ax equal to B. So all of you know that you have the Gauss-Jacobi method and the Gauss-Seidel equations. In the Gauss-Jacobi or Gauss-Seidel iteration, what you do is you take the ith equation and change and then obtain the solution, the first order the iterated solution as the residue vector of the ith equation divided by aii. Because look at the ith equation, it is sigma over j aij xj equal to bi. Okay, so if xj is all xj0, then if you leave out I, because there is a prime in the summation here, then aii xi is equal to bi minus of sigma over j aij xj0 with a prime, which means j equal to I is not included, and you divide it by aii. I don't know why there is a n sitting there. That's a mistake. Okay. Now, this is very much like the coordinate relaxation technique I talked about for solving the simultaneous equation, because here we are using a similar thing. You are trying to improve the solution of every component by component, and I have shown here for the ith component. So once you do that, what you can do is in the small matrix algorithm, you calculate, you start with Q1, which is a solution, which is an approximate solution, which is nothing but the BI divided by AII. Ignore all the off diagonal elements, then the solution is just BI divided by AII is XI. And that is the zeroth order solution. And you construct Q2, which is a first order correction to this one by calculating X1. You see, use this one to calculate X1, you know X zeros. So when you do that, you can calculate a Q2, which is nothing but X1 minus of X1 comma Q1. So this is Gram-Schmidt orthogonalization procedure divided by the norm of the vector. So now you have two vectors Q1 and Q2. When you have two vectors Q1 and Q2, you can set up a 2 by 2 matrix. So when you set up the 2 by 2 matrix, then you'll see that my equation AC equal to B can be represented as AC2 equal to D2, where D2 components are Q1B, D21 is Q1B, D22 is Q2B. Okay, and A itself is a matrix which is A11 is Q1, AQ1, A21 is Q2, AQ1, etc., etc. And then you have the set of equations which is only 2 by 2 equation, almost very similar to the Lanchos case where you had a small matrix equation for the eigenvalues. Now we can solve C2. When you solve for C2, see Q1 and Q2 are actually n vectors. If a matrix A is a n by n matrix, Q1 and Q2 also have n components. And you can write down the solution at the end of second iteration as C1 to Q1 plus C2 to Q2. Okay, because it is simply solution of this equation is the same as the solution of the AC equal to B equation. So once you get this X2, you go back here, compute X3. Okay, and from X3 you compute Q3, and from Q3 a 3 by 3 matrix equation, and so on and so forth. That means you can actually keep iterating and increasing the size of the small matrix, and you can stop increasing the size of the small matrix when it becomes too big. The latest solution you take as Q1 and restart your iterative procedure, and this is the way you actually solve the small matrix problem. So this is how we actually solved most of the equations that are there, and this is actually only good for a matrix A must be positive definite. So if Gauss-Seidel equation iteration or Gauss-Jacobi iteration should work, then the matrix A must be positive definite. But when you have E minus H cross omega, okay, then depending upon omega, the eigenvalues of the matrix becomes negative. So if it becomes negative, you can't use this reiteration, but instead you use this system. So if A is not positive, that means you take A transpose A, X equal to A transpose B, and you can solve this. It's not very much different as far as solving the system is concerned. And this one, way back in 1996 or 97, we showed that we could calculate the gammas, for example, alpha and gamma. Alpha is the polarizability. Exact polarizability for a 12-side problem was 5.343, and from DMRG we got 5.317, and gamma was 598.3. We got from DMRG 591.1, and all of these are in units of ESU, 10 to the power 24 and 10 to the power minus 24 and 10 to the minus 36 ESU. And of course, if you look at the dominant component, the error is zilch, more or less. In alpha, it is 14.83 versus 14.81. And for gamma, it is 2873 versus 2873. So this is one of the most highly accurate techniques for obtaining frequency dependent response of a Hamiltonian. Okay. Now, let me come to time dependent DMRG. So that was frequency dependent DMRG. Do you have any questions? I'll be happy to answer. Any questions at this point? I think after lunch and the ride, you must be tired, right? Because I'm feeling sleepy. So you wake me up by asking questions. Okay, so what is time dependent DMRG? If you are given a wave packet at time t equal to 0, you want to propagate it in time. And how do you propagate it in time? Just solve the time dependent Schrodinger equation. So IH cross del psi by del t is H psi. The formal solution for this is nothing but C of t is equal to e to the power minus IHT by H cross times psi 0. So if you know all the eigenvalues and eigenfunctions, any wave packet given to you, you can expand it in terms of the eigenstates. Psi 0 equal to sigma over I Ci phi, and H phi is equal to Ei phi. So psi of t, you know how it's going to be, just sum over I Ci e to the minus I omega t by H cross phi, provided the Hamiltonian H is time independent, because otherwise you will not be able to get the eigenvalues have no meaning. If it is not, if it is a time dependent Hamiltonian, then energy is not a stationary quantity. Okay, but in that case, you can also use a basis and recast it in terms of equations, which are linear equation, linear first order differential equations. If you look at Masbacher or books like that, they deal with it extensively, and you can obtain a solution for this. Well, in practice, one needs to obtain time dependence numerically, because most of the times you cannot get all the eigenstates. Okay, that's one of the problems. So how do you do it? So you can approximate the time evolution operator e to the minus IHT by H cross as 1 minus IHT by H cross plus H squared, T squared by 2H cross squared, etc., etc. For very small time steps, you may probably truncate the linear term. See, the problem is, if you truncate the linear term, can you tell me whether this operator is unitary? Okay, so if you take the U dagger of this one, it is not in, it is not going to be unitary, right? So your wave packet does not preserve its norm. If the wave packet does not preserve the norm, either you have to normalize it as you go along, or else, you lose the information. Okay, so in order to have a unitary propagation, you use what is called the Crank-Nicholson formula. So Crank-Nicholson formula uses the unitary operator, which is 1 minus IH delta t by H cross divided by 1 plus IH delta t by H cross. Okay. Okay, so here again I have missed a factor of 2. Okay, so this is actually IH delta t by 2H cross in both places. In the denominator, I should have had a 2. Okay, I'll tell you why. Delta t by 2 is what I should have had, not delta t. Now, this operates upon psi t to give you psi t plus delta t. So I can actually write as 1 plus IH delta t by 2H cross times psi t plus delta t is equal to 1 minus IH delta t by 2H cross psi of t. So you see that 1 minus 1 plus IH cross delta T by 2H cross, 1 plus IH delta T by 2H cross is actually a backward propagating operator, right? It's a plus IH delta T by 2H cross. So it will backward propagate your wave function by delta T by 2. Whereas this one is a forward propagating operator, right? 1 minus IH delta T by 2H cross. Okay. So if you forward propagate psi T by delta T by 2, you get psi T plus delta T by 2. If you backward propagate psi T plus delta T by 2, you get psi T plus delta T by 2. So the two should be equal. So all that you are saying is that when I take psi T plus delta T and backward propagate by delta T by 2, or I take psi T and forward propagate by delta T by 2, the two should be equal. And that's what this Crank-Nicholson scheme uses. Okay. So here I have written correctly delta T by 2, but the equations are wrong. I'm missing a factor of 2. This one, how it is unitary. Yeah, but when you take U dagger, it is, see, H is Hermitian. So it will be 1 minus IH, or 1 plus IH delta T by 2H cross, and 1 minus IH delta T by 2H cross you multiply. U dagger T is I goes to minus I, right? So this becomes plus and this becomes minus. So the two will cancel. I don't know, you have a board here, right? You have okay. And what is U dagger T? U dagger T is plus and then this is minus. Right? They will cancel. So U dagger equals to 1. Okay. So now in order to solve this, once again, you use a basis. So you assume that psi T plus delta T can be expanded in a basis. So if the components or the coefficients of the basis are C, the vector C, and then 1 minus 1 plus IH cross delta T by 2, that is the right hand side. Okay. If psi T, psi T is actually CT times the basis, right? The vector CT, because if I have a basis, the wave function is written by C of T plus delta T. Because C of T plus delta T is a vector, it gives you components, and the components give you the weight of the basis function. Okay. So whenever you have a eigenstate, you can write it as a vector C of T, implied that the coefficients, the components in the vector give you the coefficients for the basis functions. So what I have done is, so this one is a C of T plus delta T it gives when H becomes a matrix, and this becomes C of T times a matrix. So you have the Hamiltonian matrix here, and C of T because you know the wave function at time T, and you only want to propagate it to time T plus delta T. So because you know the wave function at time T, you know the vector C of T. So 1 minus IH delta T by H cross operating upon the vector C of T will give you some B of T. Okay, some vector B of T. And H is, of course, because it's a Hamiltonian matrix. We have already computed the Hamiltonian matrix. And on the left hand side is a matrix 1 plus IH cross delta T, IH delta T by H cross. So this is another matrix. So so I get the equation. The matrix A operating upon the vector C T plus delta T is going to give me a vector B of T. Right hand side is known, the left hand side the matrix is known. So I have to invert this equation and to get C of T plus delta T. Now it is very simple to invert it. Okay, because we have already seen how to solve the simultaneous equation using a small matrix algorithm. But the problem is for the calculations to be accurate, you must keep rather small values of delta t. So which means if you want to propagate, say, for example, t is equal to 1 nanosecond, you may probably have to solve the equation a million times. And the system of equations are like a million equations. So that is going to be rather difficult. Okay. Although crank Nicholson can be accurate, but you don't want to do it over and over again. So in order to avoid that, what are called multi-step differencing techniques have been used. In the multi-step time differencing technique, it is like this. Look at e to the minus IH delta TA plus e to the plus IH delta T. So that is nothing but 2 times IH delta T squared plus an error of the order of H delta T to the power 4. You can also write down a similar expression for e to the minus 2 IH delta T. I have taken H cross to be 1 in this case, okay? So minus of e to the plus plus 2 times IH delta T. So if I expand this, I get 4 times H delta T, 4 times IH delta T times minus 1/3 plus 2/3 times this quantity, IH delta T e to the power IH minus IH delta T plus e to the plus IH delta T, which is actually what is here. Okay. So you substitute from here into this thing, then what you will get is a technique known as the 4th order multi-step differencing technique. So it gives you take this and operate upon psi of t. What do you get? Psi of t plus 2 delta t, because you have 2 delta t is the time evolution that this operator is going to give you. And you take this one onto the right side, then operating upon psi of t, you will get psi of t minus 2 delta t. And you have here 4 times IH delta t by 2 times this quantity, which is actually propagating that wave function by t plus delta t and t minus delta t. Okay. And the error is of the order of H delta t to the power 5. So what are you seeing here? If you know the solution is t minus 2 delta t, t minus delta t, and t plus delta t, then you can actually get the solution as psi 2 t plus 2 delta t, correct to order delta t to the power 5, H delta t to the power 5 by simple multiplication. No solution of the linear algebraic equation. You see that all that you are doing is multiplying by a matrix into the vector. So I have the vector here, and I am multiplying 4IH delta t onto the vector. So I get psi t plus 2 delta t is just psi t minus 2 delta t plus 4IH delta t by 2, which is the Hamiltonian matrix, multiplying onto the states psi t plus delta t, and psi t minus delta t. So this becomes much faster and also it's accurate. Okay, if you want higher accuracy, you can construct further, and then you can show that psi t plus 3 delta t, you can have an expression like this, which is OH delta t to the power 7. But as you keep increasing this, the time step for which is going to be useful, convergence is going to be good, is going to reduce, okay, considerably. So delta t has to be much smaller as you go to higher order techniques. So we can also employ, we can also employ things like the Adams-Moulton scheme, AM scheme, which is actually psi 2 plus t plus 2 delta t inverse psi t plus 2 delta t here. You see, is in a way you can put it in here and do it self-consistently and get a much better accuracy. So you take that psi t plus 2 delta t, put it in the right hand side, you get psi t plus 2 delta t on the left hand side, then put that thing again back in here until you are going to convert. So iteratively you can get the corrected work. So you can use the MSD4 as a predictor and this one as a corrector. Okay, and this predictor corrector method is also very good at convergence, and this method is suitable for small delta t and is accurate and fast. Okay. Yeah. No. What I require here are the solutions that I've got at psi of t minus delta t, psi of t plus delta t. Okay. Then I can use the solution is psi t plus 2 delta t. So I start with t equal to 0. Yeah, 1 and 2 if you want to count. Okay. But then 1 and 2 keeps increasing because I have already done it until t. Correct. So you can get the first 3 using Crank-Nicholson. Okay. So if you use Crank-Nicholson to get the first 3, then you can continue with MSD4 and Adam mode. What's the time now?
15 minutes plus 15 minutes.
Okay, good. Okay, DMRG time evolution. Okay, so I think I spent too much time on other things. Okay. So one of the things is if you use the DMRG Hamiltonian and the DMRG Hilbert space that you have got from calculation at time t equal to 0 and do the time evolution, very quickly the wave function that you have got goes out of the DMRG space you have chosen. For example, for very short time scales, if this is your DMRG Hilbert space, this is a full Hilbert space, DMRG Hilbert space is here, then your initial state is here. So for up to a short time, it is within the DMRG Hilbert space. And as you evaluate more, it goes out of the Hilbert space. So it gives you errors. So if you do static DMRG time evolution, which was actually done as the first time evolution by Casalila and Marston. So that's only good for very short time scales. So beyond that, it just gives you too much error. So how does one do it? So in order to improve this, this thing Lu, Xiang, and Wang, okay, LXW they call it. So they used an average density matrix approach. In this average density matrix approach, what they do is at time when the system size is n, you obtain the Hamiltonian matrix from DMRG and crudely propagate it in time steps t, 2d, 2 delta t, 3 delta t up to some time interval capital T. So say, let us say you evolve it over 100 time steps. And then at each time step, you get the density matrix. So the density matrix you get at each time step is Ti, rho Ti. And then you take an average with some weighted average where the weights are alpha I. Okay. So you see that alpha I sum is 1 and Ti is T by n times I. So you calculate the wave function at Ti, obtain rho I, and then you obtain the average density matrix. And once you obtain the average density matrix, you get the eigenstates, the Hamiltonian matrix using the eigenvectors of the average density matrix. Okay. So once you get the density matrix from the, once you get the density matrix eigenvectors from the rho average, you can construct the Hamiltonian matrix. So this Hamiltonian matrix has already incorporated in it the excited states that may come because of long time evolution. Use that one to time evolve your Hamiltonian, your wave packet at that particular size, whichever it is, 100 sites or so. And then add 2 sites, go to the next one, do the same thing. So it is infinite DMRG at every step. And at every step, you time evolve it, okay, until the final time in some time steps, some 100 time steps or something like that. And then get the average density matrix, okay, and go to the next one. So until you reach the final system size. So when you reach the final system size, you get the final results, which are much more accurate than the usual static Hilbert space DMRG. So this is what is called the space keeping DMRG, and it was introduced by LXW. Then there was another kind of DMRG that was given, which was called the Krylov space DMRG. Okay, Krylov space is nothing but the space of eigenvector, the space of vectors you get when you start with some arbitrary vector and keep operating by the Hamiltonian. Okay, so here, you keep operating by the Hamiltonian once, twice, like that. So if you give me a state psi, the Krylov space of dimension L is given by psi, h squared psi, etc. up to h to the power 99 psi. Okay, so it's exactly like the Lanchos. Okay, except that you call them Krylov vectors. Okay, you also do the whole thing, you orthogonalize them, and then you obtain the basis states. Okay, so that is the Krylov space. And then you can also get a few low-lying eigenstates. Okay, so I can express my wave packet times 0 as a linear combination of a few low-lying eigenstates. Here I have taken k as the number, sigma or I equal to 1 to k, ci psi a plus some residue r. Okay, so what I'll do is this part I can time evolve because I know very well the eigenvalues. Okay, so I can time evolve them. And this part R, what I'll do is I'll time evolve using the explicit time evolution operator e to the minus iht by h cross. Because I know all the eigenvalues and eigenfunctions of H, which is a small matrix, in the Krylov space, right? So I can, express this function of the matrix H, which is e to the minus iht. I can express it as a matrix. Okay. Once I express it as a matrix, then I operate with a matrix on R. Okay. So this is very simple. Two parts. One, time evolve the major part of it using the low-lying eigenstates, and the residue using the time evolution operator constructed in the Krylov space. Okay, so that is what is done here, and I think that's exactly what I've said here. And you can also do all the other kinds of things, like you can also do average density matrix for obtaining the Krylov Hamiltonian, the Hamiltonian in for diagonalizing. Okay, so when you are getting the low-lying eigenstates, okay, you can use the Hamiltonian matrix for the low-lying eigenstate, which is constructed from average density matrix eigenvectors, and then you can also use that to obtain e to the minus iht by h cross using the Krylov space. And we can also average the density matrix at different times to improve accuracy. There are many ways by which you can improve accuracy. Then there is another technique called time evolving block decimation method. So this is a rather simple method. What you do is, if your Hamiltonian is a bipartite one, which is the Hamiltonian over odd side to even side connectivity, I to I plus 1 when I is odd, all of them commute. Okay. Similarly, even to even plus 1, the Hamiltonian terms, all of them commute. So you have G, which is completely commuting parts, and F also have completely commuting parts. Then you see that you can also use a Trotter decomposition of e to the minus ith. So what is Trotter decomposition? Nothing but e to the minus I delta th raised to power m. Delta t is t by m. Okay, so is of course accurate when m goes to infinity, but otherwise it has an error of the order of some delta t to the power some power. Okay, depending upon how you approximate e to the minus I to. So if it is f plus g of this type, then you can write down e to the minus I delta th as e to the minus I delta t f by 2 e to the minus I delta t g e to the minus I delta t f by 2 again. So it's like writing e to the power xy as e to the minus e to the x by 2 e to the power y e to the power x by 2. Exactly that. Except that the commutation error comes down to delta t cube. So now it is possible to construct higher TEBD decompositions also, much better than this. Instead of delta t cube, you can have something of the order of delta t to the power 5 and so forth, but we're not going to. Now in the TEBD algorithm, what you do is you look at the system when the system has n sides on the left, L minus n two sides on the right. So you are interested in the time evolution of a wave packet whose Hamiltonian is over L side. So n plus 1 and n plus 2 are the two sides that I have explicitly written. Now what I'll do is I can write down the time evolution part for n plus 1 and n plus 2 sides only as u tau I plus 1 u tau I plus 2 n plus 1 n plus 2 and sigma n plus 1 n plus 2. That is, it's a 4 by 4 matrix. I can write it as the 4 by 4 matrix of this function. And this h n plus 1 n plus 2 is something that is trivial because these sides n plus 1 and n plus 2, their basis states are just, if they are spins, it's just up, down, and up, down. Okay, so it's only a 4 by 4 basis state that you have here. If they are fermions, it's only a 16 by 16 basis site. And you can write down, and then you can write down the 4 by 4 or 16 by 16 matrix. And you can also write down the matrix for this one because you can diagonalize that Hamiltonian matrix and get the function u. Now you can operate on this bond psi 0 I have taken, operate by u tau n plus 1 tau n plus 2 sigma n plus 1 sigma n plus 2 on psi 0 to get chi delta t. So that is nothing but the same terms that you have here multiplied by mu the sigma n plus 1 sigma n plus 2 tau n plus 1 tau n plus 2, and you will see here that I'll have to sum over tau n plus 1 tau n plus 2 also. So I have, instead of summation over 4 variables, I have summation of 6 indices, and 2 indices I have interchanged. Now you see that what I'll do is that I define a function phi, which is nothing but summation over sigma n plus 1 sigma n plus 2, this part. Okay, so I can substitute back here in this one. So chi delta t is now, instead of what you had was psi here, okay, now you will have pi here, and instead of sigma n plus 1 sigma n plus 2, I have tau n plus 1 tau n plus 2. Okay, so I have the same chi of delta t here. And now I'll do another thing, which is called the eigenfunction prediction scheme of Steve White, in which we know very well that mu n plus 1 is written as mu n times tau n plus 1 times some summation, right? Because it is nothing but density matrix eigenvector of n plus 1 sides is a linear combination of the density matrix eigenvectors of the n sides times the Fock space states in the n plus 1 side. So I have inverted that here because the matrix A that I have are unitary. Okay, they are unitary transformation matrices, so I can just invert the indices. So I have this expression here. So I can substitute it here, and then I can get another definition B mu n plus 1 tau n plus 2 L plus n minus 2. So I get rid of tau n plus 1 by summing over that and mu n, and I can define this term, and if I put it in there, then I get chi delta t is actually b times mu n plus 1 tau n plus 2 L mu L minus n minus 2 operating upon this state. So now you see that the total number of sites is L. I have just absorbed the site tau n plus 1 into the mu, so it becomes mu n plus 1. Now what I can do is L minus n minus 2 mu that I have, I can actually express it as a product of tau n plus 3 mu L minus n minus 3. That is, I have shifted one side to the right. Okay, so what I have done is the following. I have made this, cut this somewhere here and taken out the n plus 3 side here, and I made a block diagonal with n and n plus 1. I have put them together. I have n plus 2, and this one I have written it as some n plus 3 and L minus n minus 3. Okay, so that is, I have moved one side to the right on both the blocks. So when I do that, then I can write down chi delta t in this fashion. Okay, or I can write down chi delta t as some chi mu n plus 1 tau n plus 2 tau n plus 3 mu L minus n minus 3 times the basis set. Now you see I have exposed the sides n plus 2 and n plus 3. Okay, they have become the bare sides without being a part of this subsystems. Okay, because they are bare sites, I can operate by the operator corresponding to sites n plus 2, n plus 3. So I can take hn plus 2, comma n plus 3 and operate on this one, on this thing. Okay. So like that, I can keep going until I go to the end and then sweep back. So I can do this sweeping back and forth and keep changing the time. So this is what's called the time evolving block decimation technique. So this is useful for bipartite Hamiltonians. Yeah. Approximation is basically the density matrix approximation, one thing. And secondly, the Trotter approximation. Trotter error is there. Can you please say it again? Is the approximation? So the approximation actually is in the following step. Is a Trotter approximation. DMRG approximation is in actually getting the density matrix eigenvectors, which are basically an approximation to the exact Hamiltonian. So if your M is small, your approximation is bad. If your cutoff is small, the block states.
After we apply the
Yeah. No, it is not the approximation, it's only basis function transformations. See, because I'll tell you what the basis function transformations are. See, this is exact, right? Okay, because there are two single sites. Okay, so the Hamiltonian for the two single sites is can be set up either as a 4 by 4 or 16 by 16 matrix. So this is exact. Okay, within the DMRG scheme, this is exact, right? And then I just block them together. Okay, so what I'll get up to this point, this is exact, right? And then I use this relationship. This is from the DMRG because I have expressed my my basis vector mu n plus 1. I have split into basis vectors coming from mu n and sigma n plus 1.
Okay, so in this case, we apply
Based on the DMRG. Oh, that's the only DMRG approximation. Okay, so it is like, you know, you are contracting the tensors bond by bond. So it's just a tensor contraction when you are doing the TBD this evolution. Yeah.
Here you are considering bipartite system, but H1 is to local Hamiltonian they will not come. So
yeah,
we lose some information there.
No, that is the error that you have, the Trotter approximation. This error is because of the commutation.
But before that, you took full Hamiltonian, you took a small type.
No, my name I'm assumed is bipartite or tripartite. What? Okay. So if it is not a bipartite or tripartite Hamiltonian, this doesn't work. This scheme. This scheme is mainly for partitioned Hamiltonians. Otherwise, you cannot do this. Okay. Yeah.
It is times it is constant number of eigenvectors of density matrix.
No, we don't change the Hamiltonian. Yeah, exactly that. You know, because you only change the density matrix eigenvectors, but you don't change the number of them. Okay. So there are many other schemes. Now that the chairman has gone, I can use as much time as I want. Okay, there is no limit. So, you know, LXW scheme is based on infinite DMRG algorithm. Okay, because they use the infinite DMRG. Now here I have, and the thing to use is average density matrix over the entire time interval. Okay. Now, the point is to use finite DMRG sweeps. That is, you keep sweeping back and forth to improve the wave function. See, one of the things about DMRG is that the error is not so much in the Trotter formula as it is in sweeping back and forth. So unless you make the density matrix, that density matrix of the true eigenstate, you are going to be having error. If it is a density matrix of a different size system, then the error is there, and it is reducing that error that is most important. Oh, you're back. I thought I could use as much time. No, I'm just joking. People will also get bored.
Yes, so I think we have about 10 more minutes.
About how much? Oh, that's a lot, because I'm not going to go into the details because it will be boring.
Okay, yeah, fine. So I think then we can have.
So, and then one of the things that people did were to take tentative time steps. Okay. That is, you really don't go, you just feel it and then come back. Okay. And then if it is solid, then you take the step. Okay. That's the way. So the tentative time steps, for example, if your time interval is delta t, construct the state psi t plus delta t by 3, psi t plus 2 delta t by 3, psi t plus delta t. And how do you construct it? Use the Runge-Kutta. Okay, you can use the Runge-Kutta technique because it's the differential equation solver. You have the right hand side, you just evaluate these quantities. Okay, a standard Runge-Kutta fourth order procedure. So it's fairly straightforward. And once you do that, you do the Runge-Kutta for times t plus delta t by 3, 2t plus delta t by 3, and t plus tau. And then you obtain the density matrix as an average over all these states. So you get the density matrix for psi of t plus delta t by 3, psi of 2t plus delta t by 3, etc. And once you get the density matrix, then what you do is you get the eigenstates, and once you get the eigenstates, you keep going back and forth and sweeping it and advancing the time after every full sweep or every half sweep. So once you have done that, at the end of the full sweep or half sweep, you can advance the time, and you advance time in small time steps, which is tau by 10, not the full tau. Okay, you can look at this procedure was actually given in this thing. Steve White and Saigon have given this, and compute properties as t plus tau, and then proceed to the next step. We can have several variations of this to improve time evolution. We have used what's called the double time window techniques and things like that. So, and we studied spin charge separability in molecular systems. So these things are possible. And now I'll come to just 2 slides on finite temperature DMRG, because I thought just to complete it. Imaginary time evolution you can do. Okay, e to the minus beta h. Okay, times whatever your trace of e to the minus beta h is, you can do that using imaginary time evolution. But it is good for high temperature properties, because when beta becomes large, anyway you are always doing a trottering, make a Trotter approximation. So the Trotter approximation, if the beta is very large, then you have many lattice points. You cannot really do a proper Trotter calculation. So you make delta t large. So usually it is bad. But for low temperatures, it's better to do use an average density matrix and use a large number of states. So for example, I can use an average density matrix using, say, for example, 30 or 40 eigenstates. And then I can construct the density matrix, and I can construct the Hamiltonian matrix. And if the number of density matrix eigenvectors are small, like I keep only about 50 or 100, then my matrix is only about a few thousands. So I can get the full eigen spectrum of the few thousand matrix. So once I get those eigenvalues and eigenvectors, then I can calculate any property using the eigenvector in a given state, and then thermally average it. Okay, compute the property in each eigenstate and thermally average it. And once you do that, you get the thermal properties. And we have done that, like Manoranjan has done it on many spin systems. And we also did it earlier on what are called mixed spin systems, alternating spin systems. spin one, spin off, mixed ones. So these are things that can be done, finite temperature DMRG, and they are pretty accurate. So let me summarize my DMRG talk. So I introduced DMRG technique for 1D systems. See, this is important for exams because I think Manoranjan is giving an exam at the end of the course. Okay, so there is use of symmetries. I thought it's nice to drop a bombshell. So, and I showed the connection to matrix product states, and I showed how you can generalize it to tensor networks. These two things I am not an expert at all. There are people who will talk about it in more detail. I introduced frequency dependent dynamics, real-time evolution. And finite temperature DMRG. And I thank you for your attention.
Thank you, Professor Ramasesha, for an excellent exposure on DMRG. So, time for some questions.
Yeah.
Yes.
So, in frequency dependent property, basically DMRG, is it used also for neutral excitations or not? Because I think
Yeah.
you showed the one particle excitation equation.
No.
At least what I got.
No, what I showed was excitation using radiation, electromagnetic radiation. So the electromagnetic radiation can give you one particle hole excitation or two particle hole excitations and so forth. Because only the lowest optical excited state is largely one particle hole. There are many other excited states which are two particle two hole plus one particle one hole and all other kinds of excitation. So it considers all the excitation. For example, when you do a correction vector technique, if you do an exact calculation, so we have done for about 16 sites. So it's about 1 million excited states, several million excited states. All of them are taken into account. So these several million excited states correspond to all the electrons in the occupied space getting excited to all the unoccupied states. Okay, so there is no limit on the number of excitations. The limit is basically computational GCPR.
And also in the average density matrix approach, I was just wondering that you're taking an average over different time steps. Wouldn't that be like getting rid of dynamics then? How do we
No. The density matrix does not get rid of the dynamics.
Okay.
The point is, when you have a static space, very quickly your wave packet goes outside the static space because it keeps mixing. See, when you have a time evolution, excited states get mixed into the wave packet. So some of the excited states are not accounted for in the Hilbert space of the static DMRG. So you want to include as many excited states as possible, which is possible only when you expand the space. So you expand the space by evolving it at some future time steps, construct the density matrix, and construct the Hilbert space from the density matrix eigenvectors, and use that because that has information of higher excited states which were not there. So I start with the initial wave packet itself and use the Hamiltonian, which has information of much higher excited states which are otherwise not present. Okay.
Thank you.
With the microphone, even I can't hear.
Okay. So when you used, I have to speak into this. Okay. So you used RK method for time evolution as well. So we know RK method is usually good for second order differential equations. So is it necessary for like for this time evolution, which we know is linear?
First order differential equation. Yeah, it is good because it shows in the results.
Yeah, but then using a method which is really good for second order differential
No, it doesn't
equations.
matter because basically, you have a whole class of RK methods, right?
Yeah.
So you can use for any differential equation, first order, second order, third order. There's no restriction on that.
Yeah, but this one was, this one
Was
is
the first-
usually used for second order.
Yeah, but if it is good for second order, it's better for
It is
first order.
better, but second order takes a bit more time than linear.
Yeah, but it does not take,
No.
no, that is not the time limiting step.
Oh, okay.
Okay, so that is.
Is it competitive to the other methods that you showed?
No, this is an accurate method.
But not, is it as fast as the other methods that you showed
The
for
oth-
time evolution?
The other methods that I showed you for time evolution, the multi-step differencing.
Yeah.
That is not as accurate as the
Okay.
Hilbert space. See, because you have to do the Hilbert space adaptation. So what you can do RK4 or you can do, MS4 and AM. Okay, predict the corrector or MS6 and AM you can do. So what we did in some of the calculations was MS6 and AM. Okay, even that is good. Okay, one need not go into RK.
Thank you.
Okay.